Welcome to Design for Automated Assembly. My name is Jimmy. I'm a student in Purdue Mechanical Engineering, and let me take you on a journey through this topic. So, what's the purpose of it? It's to improve manufacturing through smart product design and simpler assembly processes. What does that mean? Well, let's take a look at what it is first. What is Design for Automated Assembly? Well, it's to make sure that we have efficient automated assembly. It's to make sure that our product can cooperate with machines such as robots, pick and place machines, and output yield at high speed. Why is that good? Why do we care? Well, in manufacturing, assembly can sometimes be up to 50% of the manufacturing cost. Automation is going to be based on the speed, repeatability, and low labor costs. And having it automated, you want to avoid jams, delays, and high costs due to poor design. So these all reflect DFM principles, which we want to improve design, improve assembly, improve manufacturing, and reduce cost to make our product more competitive in the market. Now, let's look at some of the stuff that we need to understand. For design for manufacturing and for automated assembly, remember this. Fewer parts means fewer steps, which means less on the process flow, which means less machines, which means faster assembly, which means better pricing. You want to make sure that your product can integrate with multiple functions on your line so that it is easily assemblable and it's quicker. Now, let's look at some of the consumable parts. We want to standardize everything. If you have 2 different or 3 different types of screws on one assembly, well, guess what? You're going to be likely ordering from different sources, different batches. It's going to have different potential errors, and you're going to be jacking up the price of your cost instead of commonizing everything. So, if you standardize your screws, your clips, and your connectors, you're going to simplify your tool. That means you're going to be reducing your cost. And everyone loves that, especially your customers. In your design, you want your product to be self-locating and self-fastening. What does that mean? Well, that means you want to add chamfers, you want to add tapers, you want to add alignment pins. You want to make sure that it's easy to put together. So snap fits are a lot better than screws. If, however, you are required to use screws for the design, you want to follow the following 3 guides on your right: dog point, the cone point, and the oval point. These will make guiding your screws to alignment a lot easier. And trust me, screws can be a big pain in the ass in assembly, and you want to spend as little time on it as possible. Another thing to consider when designing for automated assembly is symmetry and alignment. Let's take a look at your image on the right, top right. On the right side of it, you see a part with no assembly guides. Well, if I take a brick and a second brick and put them together, how easy is it to align those 2 holes on the corners? Not very easy, because you're going to have positional deviation, and that can be very big, especially when your machine is operating at high speeds and can have minor deviations per unit. If, however, you have the guides, like on the right side instead of the left, you will see that it's much easier to guide the parts together, and they will actually align easier. This means you have less deviation and less failures. Think of it like Legos. Legos have holes and they have the bottom parts that are hollow for easy alignment. They're very symmetrical, they're easy to put together. Follow that as a standard. Symmetry is your friend. Remember that. Because that'll get into the next part, which is feeding and orientation. If your part is symmetrical, it's less likely to tangle. It's also less likely to require exact orientation sometimes. So you want to use symmetry, cylindrical, or tab shapes to help guide it along. So top right, you can see you have a difficult surface because you have this almost hockey ring style tab. It's not the most ideal for alignment because it's not symmetrical to the plane of assembly, and it's hard. It might get tangled or it might easily deform if incorrect forces apply. Now, if you made it symmetrical, it's much easier because you can make a very symmetrical part to fit along it, and it won't likely get jammed or tangled or have issues during the assembly. Bottom, you have some other couple examples with circular versus rectangular shaped tabbing. You have this tab that is different levels of height, and you want to make it somewhat even on height across so that it's easier to align. And then you have this triangular shape where you have a tab at the end to help it align in proportion in orientation to a specific um, system level design, so it's easier to assemble. These are all key features in how you want to orientate, how you want to feed, or how you want to align for the product during the assembly. For the feeder, which is the other part, is you want to remember this. The feeding cost per unit is proportional to the feeder cost. The feeding cost per unit is inversely proportional to the required feed rate. What does that mean? Let's take a look at the graph here. As you can see, as you increase required feed rate, your cost is going to go down. The faster your machine can output, the less your cost, which is great. However, after a certain threshold, if your required feed rate, let's say, is 12, but you can only go up, but this machine can only go up to 10, it's going to cost you a lot more to get the same yield out of that one machine. So what do? You add a second one and put them at the same speeds. That way you can maximize your feeder capabilities and minimize your cost. So as you increase required feed rate, remember to also increase the number of feeders that you have to maintain a low unit cost. And that's going to be key. Here's some things to avoid. You want to avoid designs that will tangle, nest, or shingle. You want to avoid delicate parts or complicating handles because that'll increase breakage, and you want to make sure that you are using rigid parts to handle in the assembly and automation. Here's some technical guidelines to follow. You want to design for a robotic gripping. So this can be a suction cup, this can be a vacuum, this can be mechanical fingers, this can be a like a plunger suction almost. All of these are going to be different types, but they will be very useful. So you want to design your surface of contact to be suitable for these types of grips. You want to ensure easy tool access. So if you need to change the tool or the fixture for it, it's easy access and you don't have to waste a lot of downtime. You want modular assemblies and sub-assemblies because this will make it a lot easier to assemble later on and easier for your machines to pick up. You want poka-yokes. You want to have inspection features. These will help guide you through the process of assembly and also make sure that your product is being assembled correctly and not outputting defects. And if it is producing some defects, you need to stop and start revisiting your design either on your assembly level or on your design level to make sure that it doesn't happen and you can have a high yield. High yield is going to be super important, and I will go into that later. But first, some other key technical guidelines you should follow is you want to make sure that your base part is very stable and it has locating features, so it's easy to assemble from top to bottom. You want to, or bottom to top, depending on how you are orientating the part. You want to avoid screws and soldering as much as possible because they can be easily prone to errors in assembly, much higher than snap fits and other simpler mechanisms. Now, let's take a look at some common modern day parts that use this. The first thing that comes to mind is a PCB assembly. A printed circuit board, all these tiny little parts. Can you imagine how they're soldered and placed? Well, it's through SMT. That's called surface mount technology. They use a lot of pick and place for micro components, and they have a lot of vacuum tools and high-speed placements to put them onto this board. I'll show you a video on basic PCBA assembly, and I think this will be very useful in understanding why dfaa is so important.
Here are Boy Electronics in Northern Italy, and I'm going to share with you now the PCB assembly process as it starts from the breadboard PCBs to the end customers. Boy Electronics have implemented a very advanced Industry 4.0 PCB assembly shop floor. As you can see, there are hardly any operators in this production floor because they have chosen to implement a very high level of automation. This is the shop floor of the future. Let's go have a look. The breadboard goes into the laser marking machine. The machine marks a unique serial number, which comes from the ERP and reports to the output file that the Valor IoT can then collect the data. The serial number will enable us to track this specific board and know exactly what happened to it. At ROY, the serial numbers are generated by the ERP and are unique to each PCB. The screen printer applies the paste through the stencil. Each job has a different stencil, which is planned with Valor process preparation. It must be precise per product and per revision. At this station, we can expect a relatively high rate of defects. It is very sensitive to environment condition, temperature, humidity, time. This is the reason for many tests and inspection after this stage. With Valor Material Management, we can conduct stencil verification by scanning the stencil barcode and reporting the exact stencil and paste we have used. The solder paste inspection machine, referenced as SPI, tests the quality of the printer to verify that everything was printed according to the plan and there is paste only where it should be. The SPI will run the test program and report the findings in a file, including pass-fail, as well as measurements. This data is later on collected by Valor IoT. Roy has three types of pick-and-place machines: a fast pick-and-place machine, a machine with a camera for small and subtle components when accuracy is highly important, and a very strong machine with high pressure for boards that require force in implementing its components. Having different pick-and-place machines is typical to many manufacturers. It allows for high accuracy and flexibility. Valor process preparation can help in generating the assembly programs. Valor IoT manufacturing connects to the pick-and-place machine and can collect data regarding machine utilization. Valor material management helps manage the material on the machine and replacement of material when it's consumed. At the visual inspection station, operators can validate that the correct components were placed on the board before continuing in the manufacturing process. Valor process preparation can create the documentation which will define for the operator what should be inspected at this stage. Here, the soldering is done. The plan for the oven is referred to as an oven profile. The reflow oven is divided into several chambers. The speed through each chamber can be different, and each chamber can have a different temperature. Valor IoT manufacturing connects to the reflow oven and receives information regarding the actual temperature and speed of the oven. At this station, we wish to ensure that each component was placed correctly in the right angle and that the soldering is good. Valor process preparation can help us prepare a test program so that the exact location where the pins contact the pads will be examined. At this point, the SMT process is complete. Following the SMT process, we have additional placement technologies such as through-hole and manual assembly. At the through-hole station at Roy, we can see that the through-hole components are placed manually on the PCB, but they're then soldered in a selective soldering oven. There are two methods which are used to perform electrical tests on the PCB. Bed of nails for high volume, which allows for shorter time of testing, but requires expensive development of fixtures, or flying probe for high mix, small volume. It takes longer to program the flying probe and run the test, but is much easier to handle new products. Valor process preparation can help plan the fixture of the bed of nail, as well as generate a program for the flying probe machine. In addition, Valor IoT will collect data from the different testers, including the different electrical measurement, as well as the pass-fail. All Valor manufacturing solutions have been integrated into the Camstar electronics suite. Data is sent to the MES, which now runs the entire process. For large BGA components, we need to check that the pins reach the right layer. These pins are usually behind the component and therefore cannot be tested with AOI machines. In this case, we use an X-ray to take an X-ray image of the PCB and make sure that the connectivity and the soldering is adequate. Now we can.
All right. I hope you saw something interesting from that and how that relates to dfaa, because as you can see, the PCBA moved from the stencil and from the location of where all the small electrical components are fed through a roller and into the system to be placed on, and then it goes into the reflow to be heated and made sure it's stabilized on the fixture or on the PCBA, right? Afterwards, it goes through some back-end testing, as you can see, with those electrical testing and the physical X-rays and all that. Those are all part of the design for automated assembly, because these designs are key in determining your product's cycle time. And that's the most important thing for this type of assembly, because your cycle time is what's going to determine your UPH at all stages. So, moving into the cost section, we are looking at mainly the cost of the feeding and orientation given this equation. So, the cost of the feeding is referring to the RF times that by 60 divided by FR. And you can see that RF is going to be equal to CF times that by your equipment to factory overhead ratio divided by the product of your seconds available in a shift times that by the number of shifts times that by your payback period in months. Depending on where you're producing this, usually in Asia it's 2 shifts versus it's 3 in the US for from 8 to, like, let's say from 8 to sorry, I'm blanking. 2 o'clock from 2 to 10, and then 10 to 8 or 6. Yeah. So that's all dependent, and these are usually will be given to you. And EO is usually 100%, which equals to 2. Unless that's specified otherwise, just assume that EO is equal to 2. Now, although that's a very micro look on the cost, in actual industry practice, from when I was an account manager, and had to look at cost breakdowns and try to understand and correct and make a correct pricing for my customer during the bidding process. Um, Cost is for this type of process is split into two types. One is the bare breakdown, which is material cost, consumables, equipment cost, logistics, facilities and maintenance, and your MVA. Very standard. However, remember with SMT, there's going to be a lot of parts going back, right? For PCBA specifically. So let's say you have a board with 50 components. Well, it's easier to calculate through the first equation, which is through material cost and separating out everything. Now imagine you have the SMT at 2,000 components. Well, the customer doesn't really want to go through every single one of them. So what did they do? They create a cost that is based on the number of components times the cost per component. And that's value is varied by industry standard. I cannot tell you what that number is because it is different for everybody. But I can tell you this, it is, you can assume that it's going to be a fraction of the number of components to balance out the cost. All this is important because you need to remember the cost will effectively be decided by the forecast and your UPH. If you have a high UPH, you can meet higher forecast demands, which is great. But that's only if you can get the forecast. If you get the forecast, everything's fine. If you get a much lower forecast, it's going to hurt you because you have an overamped machine doing the bare minimum or less than what it was intended. So you're not going to be recouping as much in terms of what you've amortized into your costs. So while there is a specific equation for the automated assembly, remember that in industry, this is generally the breakdown for cost. And this will ultimately decide how you plan your cost structure and how you design your line and your automated assembly process to fit what the customer wants and what you want in turn. Finally, let's look at the pros and cons. The pros of doing this is lower labor costs, as you can see from the automated line. There weren't that many operators, and you want to reduce that because they are much more expensive than the cost of a one-time machine. Next is the increase in consistency and speed and the higher product quality. Automating everything, you will achieve high quality. You will achieve high yield without a doubt. But in certain industries, like consumer electronics, especially for PCBs, and even like, for example, connectors or cables, right? These products require you to have a 99.5 or a 99% yield rate to pass. And you are expected to keep going higher as you keep on building and as you keep optimizing. So what does that mean? You're gonna have a lot of capital investment in automation. You're gonna have a lot of upfront cost in design efforts during the early phases before ramp. That means you need to have a lot of capex ready. You need to have the procedures, you need to have the technology down, you need to know exactly what you're doing. The good thing is that these are all very well structured and well defined in the current industry standards. So you have a lot of places to take reference from. So it is very achievable. Overall, I want you guys to remember a few things. One, I want you guys to remember the technical guidelines of what makes a good dfaa, what parts go into it, and I want you to remember the feeding requirements and the number of feeders that you'll need when designing. Because this will ultimately go back into your cost, which is going to be your selling point to your customers. Thank you.